here. And that is, let's see what we have left. Obviously, Monday you took an exam, and no, I haven't got it graded. You can imagine it takes quite a while to grading it. I've done the first one so far, and that was the one with the rod hitting, and hopefully you did your conservation of linear momentum and then conservation of angular momentum, and that's really all you need for that one. Anyway, so later today I hopefully will do number 2, and then through the weekend I'll do number 3, 4, and 5. So Monday I'll get it back to you. We can pass it back, we can go over it, we can look at that. But here's what we have left. We only have 3 more regular days, counting today. And so we've got the lecture today, Wednesday, and then when we come back after the Thanksgiving, we've got just 2 more. We've got Monday, we've got Wednesday. And the goal here then is to talk as much as we can about 13 and 14. So my plan here is to do 3 hours on 13 and 3 hours on 14. So we will do most of 13 today, and it will then flow a little bit into Monday. Then on the rest of Monday we will go into 14, and then on Wednesday will be the rest of 14. You have another lab to do. Your lab will be next Monday. It will be on chapter 14, so hopefully we'll just start 14 and do Archimedes principle, which is what the lab is, or maybe we'll do Archimedes principle first in the lab and then see it on Wednesday. That works too. But anyways, that's the goal here. That's the last part of this. Well, the good news to be said here is you can lift up your right hand, you can put it over your left shoulder, you can pat yourself on the back because you did get through that brutal test number 3 there. That was definitely the hardest part of this class, and maybe even arguably the hardest part of the whole book, the next 3 semesters. Maybe not, it depends on how things you view things, if you're more mechanically inclined or electrically inclined as we get into next semester and we see some other things here. But definitely for this semester, it's that torque, it's that rotational inertia, it's putting together conservation of energy, conservation of linear momentum, conservation of angular momentum, and deciding how to put those pieces together in order to solve the problem. And and I could see that on test number 1. People were a little apprehensive about doing this, or they did this instead of this, but I could see all the principles coming into play here. And I haven't got a chance to grade number 2, but it's going to be really interesting in number 2. That was the ball rolling down the hill, because you could use energy, or you could use your dynamics and your forces, and depends which way you want to do it. There's a lot of ways of approaching that problem. I don't know if that's good or bad. In one option, I think that's good because, hey, there's so many options. How could you do it wrong, right? Well, maybe there's too many options. But I know when it comes to grading, it's tough because I got to go, okay, which way are they headed? Why are they going this way? What are they doing? And then once I figure that out, then I can say, okay, what did they do incomplete here? Oh, they got this part right, but not that part. Anyways, that's just a long way of saying there's the next 3 days. 2 chapters, 3 days. I don't want to say they're easy chapters, but they are significantly easier than what we have been doing. They've got just a couple of main principles. This one's got 1 main principle. I'm going to put it on the board here in a minute and kind of joke with you and say, you want all the answers to this chapter? Here it is. It's 1 simple line here. But it is about that 1 fundamental principle, that 1 simple idea. And today it's going to be Newton's universal law of gravity. So we'll look at that. Then we get into finals week, and in your case, your final is probably the first one of the week because it's Monday morning at what time? 8 a.m. What time? 8 a.m. Did I say your final was early at 8 a.m.? All right, so don't miss that. Don't forget it. Don't show up at, well, you guys are here at 8:55. We'll see a bunch of other people come in about 9:15, 9:20, all right? But don't come strolling in at that time. It's 8 o'clock, and it's from 8 to 10, and we getting kicked out of here for chemistry final coming in at 11 here. So, we could push it, stretch it, 10:15, 10:20, 10:30 on the outside, but then we got to be out of here. So don't forget that final. All right, well, anyways, obviously, that's the last 4 days. So 3 lectures and 1 final. All right, so I'll go ahead and jump right in here and say, all right, what have we been doing and what's new here? Well, chapter 13 It's kind of an extension of what we've been doing. I should point out what we have been doing. If I was over here and I said, hey, let's take the Earth down here and say, okay, here is the Earth. And I said, let's take some kind of object up here. And so I said, here's the object of mass m. And I said, all right, there might be a bunch of forces on this object. One of the force is the force to gravity. What would you have said would be the equation for the force of gravity? Answer? Yeah, you would have said it was mg. Well, we're going to revisit that. Why did the g come out to be 9.8? Why did we say it was a constant? It's a bit more complicated than that, and that's what this chapter is all about. This chapter starts off, and maybe I'll just put it here on the board, another discovery by Newton. It's called the Law of Universal Gravitation. And it's to re-look at the force of gravity. And it simply says this, instead of writing it out in words. In fact, your author's done a good job of writing the words. Maybe I'll just read the words to you, but I know you can read it. I want to put it in equation form. He simply writes it this way. Every particle in the universe attracts every other particle with a force that is, and I'm going to stop right there. Here's what it's saying. Object number 1, object number 2. Any two objects. Now the reason I emphasize that is because up until this point in this class, we've done this. We've said that the objects are, some other object and the Earth. What about a second object near this first object? Is there any attraction between those two objects? Yes. And so many of you recognize this. This is no different, and I don't think we're doing anything more this semester than we did last semester in 102. But there would be an attractive force between any two sets of objects. It's not something that is magical about the Earth or something magical about the planets. And that's where I want to emphasize first. If you just have any two objects. And so it's kind of a simple way of labeling it as something like this. Object 1, object 2. Two lead spheres. Are those two lead spheres attracted to each other? Yes. Okay? And so it doesn't matter that one is the Earth, although, as you'll see, the amount of mass adds to the amount of force, and because of that, the Earth plays a much bigger role than any two separate objects. All right? So, there is the first sentence. Any two objects. I'll go on. It says here, with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. What it is saying is this. If I put this in a form and I say, okay, this object has a force on it. This object also has a force on it. Using the notation that we learned earlier, we would have said this, that these objects have a force, and that force would be labeled as force from number 2 on number 1. And this over here would be the force from number 1 on number 2. And so they would be equal, whoops, wrong one, equal and opposite. So make sure that went on there. Okay. So, and I guess that's a long way of saying here is that don't forget there are two forces, but there's one on each object. That's Newton's third law. If object 1 puts a force on object 2, then object 2 puts a force on object 1. All right. What is it equal to? Well, here is the main thrust of this chapter. Right there. The force is equal to what? It's directly proportional to the product of the masses and inversely proportional to the square of the distance. So m1 and m2 are the masses, r is the distance between them, and for rounded objects it would be center of mass to center of mass. If we have time, we'll talk about what if they're not perfectly rounded objects, but for right now at least, and that probably is all the time we'll get, is what if they're rounded objects. We're talking about from center to center. So from center to center, and so maybe I should put it this way. And so from center to center. The g is just some kind of constant. We call this the gravitational constant. It's 6.67 times 10 to the negative 11. The units would have to come in to be a Newton, meters squared, and kilograms squared. And so using the idea that the mass is put in kilograms, you'll see that it'll cancel. Using the idea that the distance will be put in as meters, you'll see that will cancel. And then the total force then comes out to be in newtons. All right? And as I said a few moments ago, that I would joke with you, and I'll say it again, you want all the answers to all the homework problems here in this chapter, and for that matter, the one problem that will show up on the final exam related to this chapter. So in case you were wondering about the final exam is, yes, you will have a question from this chapter. And you will have one from chapter 13 and one from chapter 14. And then the other 5 will be distributed from the semester here. And so we'll have that. So that's how I'll handle the fact that new material. You'll have one question on 13, you'll have one question on 14, and then you'll have 5 on the rest of the material, the bulk of the material that we've already done. Okay? And so these kind of loose ends here at the end. But I can show you, and that's what I plan to do for the next 3 hours. You know, like I said, 2 hours today, 1 hour on Monday, is everything I do will come back to that equation. And so I'll do as much as I can, but hopefully it will do enough that you'll realize that, hey, there's tens of thousands of problems. We can't possibly do them all in class, and that's not the whole point of a science class. We never try to do them all. What we try to do is enough that you'll see how this fundamental principle applies to so many different scenarios that you could apply it to a new scenario, although you've never seen it before. And that's this whole idea of the fundamental physics, applying a few basic principles to a universe of phenomena. So that's what we have here. And so I say that by just kind of beginning and saying, all right, let's do a first calculation. It's really a first calculation that is simple as this. Let's take an object that is maybe above the Earth by a little bit, maybe a meter up. And so I take this object, maybe this calculator, and I hold it above the ground 1 meter. And I say, what is the gravitational force on that calculator? Now, this calculator doesn't weigh much. It's about 100 grams. And so if I do that, or draw a picture, I guess it looks kind of like this. Here's the Earth. Here is this, well, I guess kind of looks like a box calculator here. There's my calculator. Okay, and it has a mass of about 100 grams. Now, if I were to ask you then, what is the gravitational force on this calculator? Using this new idea, not the old idea, but I do want to tie them together. Using this new idea, here it is. Okay, the gravitational force would be what? Well, it'd be capital G times m1, m2 over r squared. All right, well, we did this very similar type of problem in 102. We put in G, all right, so there's 6.67 times 10 to the negative 11, a Newton, a meter squared, a kilogram squared, all right. Then I need to put in the masses of my two objects. What are the two objects? Yeah, good. You see it. It's the Earth and the calculator. So I need to put in the mass of the Earth, and I don't expect you to have it memorized. But I do expect you to know where to look for it. Where do you find it? Yeah, that's what the cover is for, right? And then I can't remember now if it's front cover or back cover. I think it's back cover. No. Must be front cover. Must be first page. Ah, there it is. And so we got our solar system here. And they list all the planets and the distance, the radius, the period. Got a lot of information. So don't be surprised if you're going to be flipping up to that front cover as you do the homework. Because they'll be asking things. Well, what if this was on Mars? What if this was on Jupiter? What about halfway between Mars and Jupiter? What would you do there? And so you need to know the mass of your two objects. So here's the Earth. Now the calculator, as I said, is 100 grams, but I want you to notice something. Did I put 100 in there? No, I converted to kilograms. Why? Yeah, it's back to the value of G, right? G needs to cancel the unit. G is listed as a numerical value based upon kilograms. Okay? Then likewise, what goes down here? What's the distance between them? Okay, so if this is 1 meter above the Earth, is it 1 meter? No. Right, what do I need to put? Yeah, from center to center. So in this case, we would have the radius of the Earth, which is a big number in of itself. And then you might say to the center of the calculator, but you know, really, I mean, that's not the big issue. But to the center of the Earth it is. And again, looking at that front cover, you will see that it's 6.37 million meters is the average radius of the Earth. And so it's a huge number. And again, I wouldn't expect you to memorize. I just want to double check that I got the mass and the radius right. Yeah, I did. Okay. Because again, you got to look this up. You'll need to know this, and you won't memorize it. I mean, the Earth will use so many times that you probably can't help but memorize. But Venus and Mars will probably just do 1 or 2 problems. But I put a little plus here. Why? Because isn't the distance really the radius of the Earth plus its altitude, if you will? It's height. Now it's only 1 meter, so this kind of begs a question. Should I add the meter or not? Yes. All right, I guess technically the answer is yes. It's plus 1 meter. But is it really going to make a difference here? No. And I bet if it was a little higher at 2 meters, or if I took this calculator up to chemistry and did my lab and I may be now 5 meters up, do you think all this is really going to matter 1, 2, 5 meters compared to the 6 million? No. Which is why, what did we say before this chapter started about the force on an object? We just said it was mg. Didn't we say it was the same value whether it was on the first floor or the second floor? Yeah, and so we didn't pay any attention to the difference. Now, technically, does it matter? Yes, but why do we get away from it here on the surface of the Earth? Because it's small compared to the radius of the Earth. Now, could we ever go high enough that it would start to matter? Oh, yeah. And that's what's kind of neat about this chapter. This chapter is an extension of what we've been doing. Simply put, what we've been doing is we've been doing problems that basically say that don't go up very high. Of course, what's the definition of very high? Well, usually I kind of limit to what I'll call the biosphere, where we don't go very deep into the Earth and we don't go very high up into the atmosphere. But if you're only going to go 10,000, 20,000 feet, that's not going to make a difference here. I mean, even, you know, Mount Everest, we're what, in the 8,000 meters. I mean, 8,000 meters sounds like a lot, but it's just not that much. In fact, you probably even noticed it if you've ever even got higher, like in an airplane. If you've ever flown in an airplane, and a passenger airplane on a significant distance. So you're probably at 30, 35,000 feet. But I bet the last thing you thought about when you were up in that airplane is like, man, I sure feel a lot lighter. I sure feel like the force of gravity has diminished down here. I must be high enough to make that difference. You didn't notice that, because it is such a small value. So again, anything that was in, you know, what I'll call, you know, our biosphere, and even our atmosphere. I mean, even going up higher than that, you know, 100,000 feet, 200,000 feet, you know, even getting close. Well, once we start getting into an orbit, then I think we better take it into effect. And so some of these near Earth orbits at 150 miles, 200 miles, then we better consider that. But the point here is, this is the whole reason why we got away with saying it was a constant. Is it really a constant? No, and that's what I want to make sure you saw. That as you go higher, the force of gravity is diminishing. But you've got to go pretty high for that to be true. So here's the short answer, because you need to make a decision now when you look at a problem. When you look at a problem, how are you going to calculate the force of gravity? Are you going to use this, what I'll call the more complete formula, or are you going to use this older one, mg? Well, isn't the mg easier than that one? Okay, it is, but it's not as complete. So here's kind of our answer. If you're in the atmosphere, go ahead and use that one, mg. Okay, it's roughly a constant. So if you're taking a final exam and it says something about an airplane, or it says something about a roller coaster, and you've got to calculate forces of gravity, or maybe even gravitational potential energy, what are you going to use? mg, that's fine. But if the problem goes further than that, if the problem says we have a rocket ship that now goes into orbit, are you going to use mg for the force of gravity? No. What are you going to use? This new one here, the universal law of gravitation. Okay, so there's step one. New formula. When does it replace this one? Higher than the atmosphere. And for that matter, into the Earth too. Because as we go into the Earth, some very interesting things happen. And like I said, we'll probably run out of time to really do too much about going into the Earth. But that's okay. We'll cover it in later semesters. It just won't be this semester. See, watch this for a second. Let me do a quick calculation. If I get out my calculator and I multiply this universal constant here times the mass of the Earth, the radius squared, but leave the mass alone, so I'll put the mass by itself here. I wonder what these three numbers would come out to be. Yeah, 9.8 meters per second squared. So that's what I was saying earlier. This will give us some insight of why it came out to be 9.8. That's what we have here. In other words, this little g was really an experimental value. We just put an object out there and we dropped it, and it came out to be 9.8 only because it was these factors, which would be the size of the Earth, the mass of the Earth, and this universal constant. Those work out to be 9.8. So that's why we said on the Earth it's 9.8. Would it come out to be 9.8 on a different planet, say Mars? It would, right? But let me ask you this. Using the front flap, could you tell me the acceleration due to gravity on Mars? Sure. This would be the same. That's why we call it a universal constant. The mass would be different, but there it is listed. The radius would be different. Yeah, but there it is listed. Get out the calculator and you find the acceleration. So, if we had a test problem that said a professor takes a pen, throws it at 45 degrees at 3 meters per second on the Earth, where does it land? Now repeats the experiment on Mars, where does it land? You could do that, right? You would have to be doing your projectile motion together with the new information, which is how do you get the acceleration on this new object, which in this case is Mars. Then we could do it on Jupiter, and we could do it on Venus. All right, well, in this case, if I actually finish the calculation, the 0.1 comes out then to be roughly 1 Newton. And obviously I wasn't interested in the total answer here other than just to get a chance to go through a calculation and get a chance to talk about it, because again, as much as I like to joke with you, I like to emphasize I'm serious. What really is in this chapter? That's it, that equation. And that equation allows me now to find the force on this calculator, because this could change. I don't see why I would, but if I was so fortunate to be able to go on this huge rocket ship, maybe I'd take my calculator with me. What is the force on this calculator now that I am much further away? And so here is my calculator. Maybe this calculator and I have gone really far. How about just 6 million meters itself? So we're the radius of the Earth up, and so if you're looking here at the Earth, you're saying, well, how far are you from the center? Well, on a scale-wise, I guess I'm this far, so out here. Now, to give you some kind of clue, let's look at California here. Here's our Santa Barbara, here's our California. And if you can see from your distance, California has a width of about 300 miles. And that's about the height of the space shuttle when it used to go up here, but they'll call it the International Space Station. So sometimes I think we forget that these orbiting objects that we put up here, they're right here. That's how high they are above the surface, the width of California. So in terms of the size of this globe, they're not that high. Okay, so I'm talking about a significant distance up here. You know, I'm talking way, way, way up here. And so again, how much does this calculator weigh? Well, I'll run through the numbers, but I think you can do the calculation, but I'll do it real quick. But the question is, will it be the same? No. Less? Yeah, it'll be a lot less. Probably about 4 times less, because I've essentially doubled the distance. And so we see this as distance squared. So if I double the distance and I square it, we're probably about a 1/4. So this came out to be about 1 Newton. Well, I'm expecting to get about a 1/4 of a Newton here. And so as I calculate the weight of it now, I would have G m1 m2 r squared. My G is my 6.67 times 10 to the minus 11. Again, noting my units are kilograms and meters, I need to put the mass in kilograms, and so there's the calculator. And also I need to put distance, which is 6.37 plus another 6 times 1,000,000. So I got to add those two together. So I've got the radius of it and then another 6 million meters. So I'm going to add those two together. And then square that distance. And so what does that one come out to be? And like I said, hopefully it's around a 1/4. Maybe I'll do the denominator first, so I can go the 6.37 plus the 6 makes a 12. If I multiply that times 10 to the 6th, I get a huge number. Square that, I get a huge number. Reciprocal of that, okay, good. Then I'll go across the numerator, times 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24, and then finally times a 10th, coming out to be 0.26 Newton. So not a surprise. It does seem to match what I thought. Okay. Well, again, and maybe those are so obvious I should move on here, but that's the simple case. That again is, this is what's new. And so hopefully you see how it's an extension of what we've been doing, because that's really the rest of this chapter. Let's look at a couple of other things here. For example, what if the problem was a little more complicated here? What if instead of having something as simple as the one object being pulled down by the one other object, like the calculator and the Earth, what if this was something such as the Earth and then the Sun and then the Moon? And so we have our little planetary model up here. And again, they don't have to be planets. They could be any 3 objects. But in that picture, I guess it kind of looks like maybe that. So I've got the Sun over here. Here's the Earth. Here's the Moon. Don't worry about Venus over here. I didn't include Venus, but maybe we should add that in just a second here. But couldn't I ask this question? What is the net force on the Earth? Right? How are you going to do that? Yeah, do you see there would be a force between these 2 objects? A force between these 2 objects? That's 2 forces on the Earth. How do you get the net force? Yeah, add those 2 together. Exactly. So maybe I would label it this way. I would say, okay, this would be the force. It would be the force from the Sun on the Earth, kind of using the author's notation. There would be another force on the Earth right here. It would be the force from the Moon on the Earth. Okay. And so those would be the 2 forces. How would I calculate this force from the Sun on the Earth? Well, I guess it would be G times the mass of the sun times the mass of the earth divided by the distance between the sun and the earth squared, right? How would I get the force on the earth from the moon? Well, I guess it would be g times the mass of the moon times the mass of the earth times the distance squared between them. And so I'll have to come back to this little chart and look them up. And to get the net force, I would have to worry about their components and their angle. I didn't really give an angle up here, so maybe I won't complete the whole calculation here. But I think you can, right? That's that whole idea of adding forces together, getting the net force. That was the whole idea of, well, Chapter 3 together with Chapter 5. Chapter 5, we learned about net force. Chapter 3, we learned about vectors. And if I put in the numbers, of course, this is the 6.67 times 10 to the minus 11. Mass of the sun, I want to say 1.99 times 10 to the 30th, but we'll have to look at that. Again, don't expect you to memorize it, but know where it is. Okay, there it is. Okay. Mass of the earth, that's the 5.98 times 10 to the 24th. Distance between them, well, that we need to look up. I think 1.5 times 10 to the 11. Yeah, distance from sun. So 1.5 times 10 to the 11 meters and square it. Okay? And so I can get out my calculator, and I was gonna, but I think you get the idea. Also, I think you're seeing, does this look a little easier than the stuff we've been doing so far? Yeah. Don't worry, we'll get a little harder here before the day's over, but it won't be as hard as that other stuff there. But that's the force between the sun and the earth. And then likewise the moon. The moon, we can do the same thing. The 6.67 times 10 to the negative 11. Mass of the moon, it's like a 22 or something. Moon, 7.4. 7.4 times 10 to the 22. Mass of the earth again, 5.98 times 10 to the 24. Distance between them. What is the distance between the earth and the moon? Where do they put it? Earth-moon distance. 3.8 times 10 to the 8th. 3.8 times 10 to the 8th in quantity squared. Okay? So again, I can put all those in, and that would give me the magnitude. And then you've got direction and all those good things. Yeah?
Are those distances between the centers?
Oh, good point, good point. Yes, in both cases. One case, to put the right distance in that equation, we need to be center to center. Right? And then that number that they list is center to center. You don't need to add the radius of the planet or anything. They're not doing surface to surface type thing, but no, they are listing center to center. So, and for just that reason, because that's probably what you need, is center to center. So they list it that way. If you wanted to know surface to surface, then you would subtract off the radius, you know, take this distance and subtract off the radius of the earth and the radius of the sun. So we could get surface to surface distance, but seldom do we want that, so that's why it's not listed. Find it, yeah, but it's better to list it the other way. Well, anyways, there's two. And maybe I don't even need to talk to you or show you. What if you had 3 objects out here? Right, there would be just a third force. You'd calculate that. Again, to get its net force, you would add your vectors together. So again, taking the stuff we've already learned about vectors and net force, we could then just add to that a new way of calculating the force here. And so even though the equation only gives us the force between 2 objects, don't think of yourself as limited to 2 objects. And that is different than we did in 102. I think every problem we did in 102 only had 2 objects. We didn't have 3 objects. We didn't have the net force. We didn't have the I and J components on calculating it. Now, well, with that said, where might this become useful? Well, let's put a couple of things together. Like I said, there's really nothing I'm going to say that doesn't really boil down to this. But I can put it together with other chapters. For example, let's say we put up a satellite. And this could be an artificial satellite, or this could be a natural satellite. Now, natural satellite means, if you're not familiar with the terminology, is something that naturally orbits. So our moon, this moon, is a natural satellite. Nature put it there. Of course, we send up other satellites, artificial satellites. But the behavior is exactly the same. In fact, that's what this whole idea is. How would you then figure out what you need to do to make something orbit? Whether it be an artificial satellite or whether it be a natural satellite. Maybe we should talk about just the moon here, the natural one. How come the moon doesn't hit the Earth? I mean, how would you describe it in terms of motion, both in equations and description here? Yeah, in other words, is there any force of gravity on the moon from the Earth? Yeah, there is. It's not like there's no gravity out there. There is a gravity. But how come the moon then doesn't hit the Earth? Yeah, it's because of the motion involved. And so if here's the moon, which is always lit on one side, interesting enough, and here's the Earth, this thing goes around, but there is a force of gravity. Now, granted, when the moon's out here, the force of gravity is not the same as if the moon's down here. So we're going to have to put this in. I am not going to say the force on the moon is mg, am I? I'm going to say it's capital G, m1, m2 over r squared. But if the moon wasn't moving, it would do something like this. Okay? They would be attracted. But it's because of that motion, it's because it's moving sideways, that the moon ends up doing something like this. It moves sideways and gets pulled down. And then it's moving this way and gets pulled down. And it's moving this way and gets pulled down. So is there a force? Yes. But the force is a little different in the sense that it's not pulling it towards the Earth, it's making it change direction. I'll put a picture on the board that we did a long time ago. We did this back in chapter 6. We said, look, if you took an object, and I think back then when we did it, we were, you know, World Series thing, so it was this little baseball. And we had this baseball, and we said, look, if you had a baseball moving this way, and you applied a force in the direction it's moving, what would that force do to it? As opposed to a force this way, as opposed to a force that way. And so I heard you guys say, this one would do what? Well, they all accelerate. So don't say accelerate. But that would make it go faster, right? What would this one do? Slower. And what would this one do? It'd make it turn. So they're all in acceleration. Whether you change your speed or change your direction, it's an acceleration here. But that's what the breakdown was. And what we really have then, and this is Newton's kind of description of how an orbit works, is he said, look, you take the Earth, or for that matter, it could be the sun and the planets going around the sun. But if it's the Earth and the moon, then you have this object I'll call moon, and there is a force. There is a force of gravity right here. But the object is moving this way. So the force is perpendicular to its movement. What that does is change its direction. So a moment later, the moon is now here. Well, the force and the movement are still perpendicular to each other. So it doesn't go any faster, it just keeps turning. And so it keeps going around, turning every time. And the force of gravity is applying an acceleration. But an acceleration that doesn't make it go faster, but an acceleration that makes it turn. Now that's for a perfect circular orbit, and that's all the time we'll get a chance to talk to about today. For those of you who maybe have a little more background in astronomy or have taken our astronomy courses, will know that the orbit is any more elliptical than it is circular. But it's really close. It's not that elliptical. And so these orbits are pretty close to a circle as the moon goes around. Or for that matter, as the Earth goes around the sun. It's almost a circle. There's a slight change. I think it's 91 million miles on the closest and 95 when it's furthest away. And so we often say it's an average of 93 million miles because it does get a little closer and does get a little further. As a side note, what time of the year does it get a little closer, do you know?
Wait, doesn't it go in the winter?
Well, you might be able to see it here. I don't know if you noticed on this gear system. This one, it's a little closer. 6 months from now, it's going to be a little further. Okay, and so, whoops, I guess I didn't get all the way. There we go. And so this, so what time of year is this? Yeah, it's summer. How do you know? Yeah, see the tilt of the Earth. So here we got it's tilted on to the northern hemisphere. Lots of sunlight. So it's summer for the northern hemisphere, but winter for the southern hemisphere. 6 months later, it looks like this, and so it's a little closer, but it's a little closer during the winter. I think it's off a little bit too, because I think it's closest in January, but this winter solstice is near what, Christmas there, like December 21 there and there. So I think our gearing might be a little bit off, or maybe well, need a little bit of adjust here. Anyways, but didn't mean to get too much into the astronomy. I'm after the physics, but obviously it's this physics that leads to the planetary motion, which explains all of our astronomy here. And so we do have a slightly elliptical orbit. And like I said, I'm just mentioning that in passing. It'll be hard enough for us to do some motion with a circle, and that'll be good for us. I want to talk about circular motion only. But I did want to point out that the orbits really can be much more complicated. They can be elliptical in nature. I guess a small thing of this, I heard somebody say here that notice that the seasons then are determined by what? The tilt of the Earth, not by the proximity. So this is winter for us. This is about where we are. I mean, we're getting close to the winter solstice here. We're about a month away here, and so we're getting close to this position. And so we're tilted away, and our view of the sun is low in the sky. And right now, you'll see it go, across the ocean, very low in the sky. So we get very little sunlight, and because of that, we get very little warmth. But we're also very close. The upshoot of that is then we have winter, but we're close to the sun. That's a lot better than the southern hemisphere. When is their winter? Yeah, their winter is when they're furthest from the sun. So their winter can be a colder winter, and their summers can be a warmer summer. Although that doesn't explain everything, because a lot of that can be influenced by local effects. How close are you to the ocean? How far are you from the ocean? Blah, 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 blah. But in general, and again, it's not a fair comparison, but in general, the Antarctic is much colder in the winter than the Arctic is in the winter. And one of the reasons, and maybe not even the major reason, but one reason is right here, because its winter is 4 million miles further from the sun than the other way around, the winter in the North Pole. Well, anyways, I probably spent too much time there. Let's look at circles, because as I said, I want to take this equation and literally keep showing you this is the equation for the chapter. This is the whole idea right there.
Do we have to commit any of the numbers to memory other than that formula? Like maybe G or something?
Oh, the capital G?
Yeah.
All right, I'll say yes, commit G. I mean, G is a universal gravitational constant. So usually what happens is the following, is I say commit this to memory. I mean, it's universal. The mass of the Earth, no, that's just a consequence of the Earth. I would give that on the test. Mass of Mars, I'd give that. I don't expect you to memorize all those. But the universal constant, that's a different story. It's true for all the planets, everything in the universe, so commit that one to memory. And then if you forget it, well, I'll come up and beg for it, and I'll put it on your paper there. But the starting point is, I would say, you need to memorize that one. So memorize the G, 6.67 times 10 to the negative 11. Okay. All right, but there's that force on the moon. Now, if the moon is going in a circle, or for that matter, a satellite going in a circle, or the Earth going around the sun, what else must that force be equal to? What did we learn back in chapter 6 about something going in a circle? Does this look familiar? All right, so what I'm really saying is let's take this new material, let's put it together with our old material and say, look, if you had something going in a circle, this is what we learned. We learned that the sum of all the forces on that object have to add up to mv squared over r. Remember those types of formulas that we did? I know it's been a while, but we did a lot of things going in a circle. And that was the whole idea of the net force. Take all the forces. Now in this case, all the forces is just one. It's the gravitational force. So I can set those two equal. Now it begs some question here. When I look at my two objects, if I call this Earth object 1 and I call this orbiting object number 2, again, whether that be the moon or the space shuttle or some other satellite out there, what m is this one? Is it 1 or 2? Yeah, it's 2, right? It's the one going around. So we are going to have to think a little bit back to chapter 6 and go, okay, what did we mean in that chapter 6 formula? What we meant is this is the mass of the object going around. So if this is the Earth and this is the moon, then this one happens to be the mass of the moon, the one going around. Let's look at the r's for a moment. What did this r mean back in chapter 6? Yeah, the radius of that orbit. So in this case, it would be from the center of the Earth out to the center of the object. And what does the r over here mean? From center to center. So they came out to be the same thing for this case. So I can cancel at least one of them off of here, and I can also cancel off the m2. And here's why I've done that. Because what I have then is I have v equals the square root of g m1 over r. Do I put a box around it? Maybe I'll put just a circle around it instead of a box. Because I get the feeling if I put a box around it, you're going to think, hey, it's real important, I'm going to memorize it, and I'm going to commit this to memory. But no, did you see where I got it from? This is what I want you to commit to memory. This is the universal force on it. This one you've already committed to memory. This is the circular moment, okay, as it goes around. And so this would be the speed. Now let's look at this. What is it really saying then? Well, it's saying this is the speed for a perfect orbit. What if it was going, say, slower than this? What would happen? Yeah, see, it's not going fast enough. It would, instead of make this nice motion and fall, I guess it would do something like that. And so we don't have enough speed. What if it has too much speed? Yeah, it kind of flies away from it, although that's when we get into a more complicated orbit because, I'll change colors here. This is if it was going too fast, I guess would do something like this. But throwing an object up or any object away from the Earth, what happens as it moves away from the Earth? Doesn't it slow down? So even though it was going too fast a moment ago, as it moved further away, it now begins to slow down. So here's where it gets a more complicated orbit. It slows down, comes back, and you start to get your elliptical orbit because of that. If it's going really, really fast, it's never going to come back. We'll talk about that in just a moment too here. But the point is, this would be the speed needed for that perfect orbit right there. A perfect circular orbit. And let's see what it's saying. As objects get further out, like say the moon. The moon's really far out there. Remember that I mentioned this earlier, that where's the International Space Station in perspective? About 300 miles, about the width of California above it. Where's the moon? Yeah, it's about the length of this lecture hall. There's the Earth. Here's the moon. Okay? And so in perspective, we get an idea of these distances. The moon's really far out there. Okay? So, in case you didn't already know, which is further out? The International Space Station or the moon? Clearly the moon, right? So what does that say about its speed, though? Do you see that? What would you say about the speed of the moon compared to the speed of the International Space Station? Which one's going faster? Yeah, the small r, right? The International Space Station. So the International Space Station has a smaller r and is going much faster than the moon. Kind of makes sense. Again, if you know a little bit about, I think you know about the moon. How long does it take for the moon to go all the way around? Yeah, that 28, 29 days. Takes a month, right? How long does it take for the International Space Station to go around?
Like 7 hours?
Yeah, and you know, I'm not sure either. I guess we could probably figure out how high it is. But I think it's around that 300 miles. And so I think it's just a couple hours. Is it much as 7 hours, somebody said?
That's what I thought.
Yeah, well, but in that neighborhood. Less than a day, definitely, is my point. It's going much, much faster than. And we could do a calculation with that. And if we do a calculation, which we will, we could get that number. In fact, let's do time frames too. Because if we kept working with this a little bit, wouldn't this say that velocity is the circumference divided by, and I'll put a capital T for the period, the time to go all the way around. And so what I have here is a square root of g, mass of the Earth, radius of the orbit. I then got a 2 pi r and I got a t. Let's get rid of the square root by squaring everything. So I get a g, I get an m1 over r, I get a 4, I get a pi squared, I get an r squared, I get a period squared. Let me cross multiply here. So I get period squared times capital G times m1 equals 4 pi squared r cubed. And maybe I'll make one more step just to solve for the period, but it's 4 pi squared over a capital G over the mass of the object radius cubed. And maybe I'll put, not a box, but a circle around it. Because again, I'm not interested in you in memorizing this formula, but couldn't you figure out what the period it takes for something to go around based on how far out is it? And sure, there it is. How far out is it? You can get the period. Or you could get the mass. In fact, it brings up the question, how do scientists figure out what the mass of the Earth is? Put it on a scale? Just kind of put it on a scale? Where do they get it? Well, you're looking at it right here, right? Don't we know how far it is to the moon? Don't we know how much time it takes for the moon to go around? The only thing we may not know is the mass of the Earth. Perfect calculation. Look at something orbiting an object, set it into here, plug in the number, boom, there's the mass of the Earth. We can do the same thing with the sun. How do you think we get the mass of the sun? Oh, good. Nobody said put it on a scale.
Count the atoms.
Count the atoms. No. Same thing. Do we know how long it takes for the Earth to go around? Do we know the distance? So can we calculate? Then the mass of the sun. So we can just look at something orbiting it, and we easily get. So it's easy to get the mass of these orbiting objects by putting together a couple of ideas, which I said was universal law of gravity, in this case centripetal force, in this case our definition of velocity, and you put it all together and you get a relationship. Many of you, if you've taken astronomy or seen it, this was actually discovered by Kepler, so we call this Kepler's third law. And he noticed that the square of the period was proportional to the cube of the distance. And so as he looked at the numbers, he didn't know why. He did not figure out this connection, but it gave him a stepping stone for Newton to figure it out here. And that's what we call today Kepler's third law, or maybe we forget about poor Kepler and don't call it anything. We just say, hey, it's a consequence of Newton's universal law of gravity. But clearly we would have it. So, but again, notice that more distance means more period. And we can put those two together. And so we can look at it. I mean, let's look at something like the sun here. You probably already know the pattern. I mean, if you go from the sun, what's the first planet? Mercury. Next? Venus. Third rock from the sun? Earth, right? Next rock? Mars. Then we get to the big gases. Jupiter, next one. Next one. Uranus. Yeah, next one. Neptune. Last one, if we can call it a planet anymore. I guess we can't, right? It's not a planet. And good old Pluto. And again, not being an astronomy class, but I learned it in my astronomy class is my very excellent mother just served us nachos and pizza, but I guess the and pizza doesn't count anymore. So, but there's the order of the planets. But looking at them and looking at this result, what is this saying? The ones further out, like Pluto, would take longer to go around than the ones closer in. And if you go through that chart, you'll see it. It'll list Mercury here, 88 days. Venus, 250 days. Earth, I think you know, 365 days. And I don't know the other ones, except for Pluto. It's like 248 years to go all the way around. And so you can see the numbers here. And so if we know the period, we know the distance, or if we know the distance, we know the period as we work it out here. But again, in all seriousness, did you see where it came from right there? I haven't done anything in that step that you couldn't have done by just taking this new material and putting it with the old material. And so there's our universal law of gravity. So we can get the speed of something orbiting. We can get the time it takes for something to orbit and the connection, of course, between its speed and its radius. And so your author has a couple of sections on that and even mentions a little bit about Kepler and his work. But I think where we need to spend the most time, really, is probably back here, and maybe I'll just kind of clear off the board here, is with the energy. The gravitational potential energy. Because didn't we already do gravitational potential energy? We did, didn't we? I mean, we dealt with potential energy back in Chapter 8. But we better relook at that, because what did we assume back in Chapter 8? Yeah, it was the same thing that I was trying to show you when we started this. Didn't we assume that the force of gravity equals mg? And I ask you again, does the force of gravity always equal mg? No. Now, go ahead and use it if you're talking about working within the atmosphere. So, I should probably put over here, what did we do back in Chapter 8? Well, we did this. We said, what was the change in potential energy? We drew a little picture over here, and we said, okay, here is the Earth. And we kind of drew a flat line, not that we really meant that the Earth was flat, but that we were close to the Earth, that it had the appearance of being flat. And we took an object, and we said, okay, if the object started right here at some initial position, why not, or why I, initial, and we moved it to some final position, could you calculate the change in potential energy? And we said, yeah, it was an integral from its initial position to its final position of the force of gravity dotted with the distance that it moved. Well, in this case, here's what we did. We said, here's the minus sign, and we made a decision here that we said that the force of gravity is mg. We said that it would be in the negative j hat direction. So when you took a dot product, which would have an x movement and a y movement, we came to the conclusion that as far as the x goes, you get a 0 because there is no force in the x direction. And as far as the y direction goes, it's a dy, an mg, an integral with a plus sign. And then, as we went from initial to final, we got mg y final minus mg y initial. Now that's hopefully review. And part of it I wanted to review so you remember what we did and see how it is going to affect what we're about to learn next. But also it's just a good time because I know you're thinking in your mind, hey, I got a final exam, it's coming up. And so I know you've been reviewing all this last week and you've been reading all those, and I'm sure you just went through Chapter 8 last night in preparation. I'm joking, of course, but this is that crunch week. So truth is, you probably have 3 tests this week. You had one, you had chemistry and and calculus. All right, so you can start reviewing after your Thanksgiving dinner there. So make sure you help out your mom, get the table set. Eat fast and then go study. All right, no. No football, okay? Record all the football ones. You can watch that after the final. All right. No. All right, well, I'm joking with you, obviously, here. But I do want to recall your memory back to Chapter 8. I want you to see what we've done. And I want you to see that what we're doing is not going to be any different. It's going to be an extension of what we did. It's a way of saying what we did was not wrong. It was just not complete. So what was not complete about it? What would be different now that I've left Chapter 8 and I'm now here with a little more education in Chapter 13? Well, the answer is the force of gravity equal to mg? No, it's not a constant. But let me help you out here, especially as you get ready to do the final exam. When would you treat the force of gravity as a non-constant? Yeah, out of the atmosphere. So again, just because I'm showing you something new, I don't want you to use that something new if we're talking about a roller coaster and you've got to do the potential energy of a roller coaster or the potential energy of a ball rolling down the hill. When would you use what I'm about to show you if we went higher than the atmosphere? That's where it matters, out into outer space here, and as we change that. So again, this mg is not wrong. It is just an approximation. It's what we would say it's not complete. So continue to use it, because I know that always comes up during the final exam. Students read a problem and they go, you know, this was an easy problem back when it was just what's the speed of the ball when it rolls down the hill. I mean, the hill was only 1 meter high. And what's the speed? Go ahead and use mg for that. Don't make it harder than that. The mg makes it easy. What we're doing now is only needed if you go significant distances. So let's talk about that. Let's talk about significant distances. Instead of me throwing a ball in the air, now I'm going to put up the space shuttle or the International Space Station or some other rocket. That's going to go way, way up there. So then what would I do? Well, let's do the same thing. I would calculate the potential energy. It would be minus the integral from some initial to some final. It would be then equal to the force of gravity, dotted with the distance you moved. Oh, let me draw a picture like we did over there. My picture, I guess, would look something like this. Since I'm going to be moving a greater distance, I'm going to stand back and get a picture of the Earth. But I might start right here at some initial position, and I might move it up here to some final position. What I will do a little different is here I labeled my height with a y. I might be better off not to call it y. What should I probably call initial distance? Would it be okay if I use an r? And I think it's better. Why an r? Yeah, because wouldn't it be the same thing as if I had started here and moved to there? See, it's an issue of moving away from the center of the Earth. It's an issue of increasing your radial direction from the Earth. And so it's not a linear vertical motion. It's away from the Earth. So I'm going to make that change. That's minor compared to some of the other changes here. But that's my first change. Is I'm not going to call then, and I'm not going to have a formula that has a y in it anymore. I'm going to have a formula that has an r in it, because it's moving away from the Earth. Okay. Now that's kind of helpful, because then when I do this and I do my dot product here, I can put in this new universal formula here, which would be a g m1 m2 r squared. But what direction is the force of gravity? I mean, going back to chapter 8, we said which direction was the force of gravity? Well, we put its magnitude and then we said it was in the negative j hat. What should I have here, you think? Yeah, negative r hat. Good. So I'm going to put negative r hat. And I don't think we've used an r hat this semester. But hopefully by analogy you'll see. What do I mean by r hat? Yeah, in the radial direction. So the force of gravity would be radially inward by this statement. It would be saying inward, 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 inward. Okay? And the same thing that this negative j hat is saying downward, 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 right? All right, so that would be the force of gravity. And which way am I moving? Well, I'm going to move straight out. Keep it simple. I'm just going to go radially outward. So my dr is an r hat. It makes the dot product easy because an r hat with an r hat is the same direction, kind of like the I hats with the j hats. So I get the two minus signs that cancel off, and I get what would be so far this, that the equation for the change in potential energy is an integral from initial to final of g m1 m2 over r squared dr. Unfortunately, it comes out to be a pretty easy integral. Not quite as easy as this one. This is probably the world's easiest integral, right? Just integration of mg is just mgy. So if I integrate this, what do I get? Okay. Yeah, I heard a couple of right ones and a couple of wrong ones there. Okay, but when you integrate a square, an inverse square here, you know, it's the what is the integral of 1 over x squared dx? That is minus 1 over x, right? So you add 1 to the exponent, so a negative 2 now becomes a negative 1, and then you divide by that negative. So there's my integral, and then I would be evaluating it from some initial to some final. So the answer I get here is minus g m1 m2 over r final minus a negative g m1 m2 over r initial. And here's the point I want you to see. The old formula for potential energy right here was mgy, and then we would put in initial and final. What's the new and improved formula? Potential energy is what? G m1 m2 over r. And I'll put a circle around it because I must admit this one looks very different than that one. And it's got some interesting properties that are really very useful, but it's also got some that are a little challenging to the beginning student here. And so, but I just wanted to emphasize here, and I'll say it again. When would you use this one versus this one? Yeah, when you're talking about huge distances, when you're going out of the atmosphere. Okay? If you only went at the radius of the Earth and went up 1 meter, you could go through a lot of work calculating this, and guess what you would get? Exactly the same thing as this one. So again, use this one. Much easier. But here's where we really have to be careful. Remember when we did Chapter 8? And I said, well, when we make this statement, we're choosing down as negative. So every time we use this formula, don't we have to have down as negative? But there was something we didn't choose. Remember in this one we did not choose where y equals to 0? So when we started using this formula back in Chapter 8, didn't we have that freedom to choose y equals to 0? And wasn't that kind of convenient? Didn't we take advantage of that a lot? In fact, so much so that I want you to be careful here. Do we have that freedom anymore? No. Where does r equal 0? The center of the Earth, or the sun, or whatever system we're talking about here. So be really careful with that. That has gone away. And we've used it so much here that students want to use it here. They go, oh, I will call r equal to 0 on the surface. Here's my rocket. Starts on the Earth. Goes up. I'll call that r equal to 0. Can you do that? Absolutely not. And you see it right here. Again, this is why I kept saying I'm a fundamental believer in fundamentals. How's that? That you got to really come back to these basics. I know some students don't like, don't make me do a derivation. Don't let me read about the derivation. Just give me the equation. Let me plug and chug into it. Oh, such a dangerous road. You're gonna make mistakes. You're gonna use it at the wrong time. You're not gonna understand where it comes from. You gotta go back to that fundamental belief, the fundamental derivation of it. And so you see it here. This one, use y equal to 0 anywhere you want. Hasn't been chosen yet, but right here, when I use the force between the two objects, I have just chosen that this is how we measure R. We measure the R from the center of the object to the center of the object. So be really careful with that. You have no choice. R is the center to center. It's been made for you right here. Don't mess that up. Also, look at the sign value, if you will. I mean, let's say that this object was on the surface of the Earth. How about if we just take me? Oh, let's go back to this calculator, because if I use me, I have to tell you my weight. That's embarrassing. So, all right. So, let's use the calculator again here. What if I said this? Here is the Earth, and here is the calculator sitting on the surface. It is on the surface of the Earth. It is down here on the ground. What is the potential energy of that calculator? Is it 0? No. I mean, it only comes out to be 0 if you define y equals to 0. But it wouldn't in this case. Now, with that said, I guess I should be very clear here. If this calculator is only going to go up a couple hundred feet, then go ahead and use that and call y equals to 0. But I'm not talking about that. I'm talking about this calculator on a rocket ship. And this calculator is in this rocket ship on the surface of the Earth right now. In a minute, it's going to blast up and go to the moon. And so I want to know the change in potential energy. How much energy do I have to give this calculator to get it to the moon? And going that far, can I use this? No, I must use this. And can I call the surface 0? No. I mean, let's do a calculation here. And so this would be saying that the initial potential energy is G M1 M2 over R initial. So it is negative. It is 6.67 times 10 to the negative 11. The mass of the Earth is 5.98 times 10 to the 24. The mass of the calculator is 100 grams. The distance I am from the center of the Earth is that 6.37 million meters. So, if I grab my calculator, I guess I have to pick it up off the surface of the Earth here, but if I put in my 6.67 times 10 to the negative 11, and my 5.98 times 10 to the 24, and my tenth of a gram, and I divide that by 6.37 times 10 to the 6 squared, I get a potential energy of that doesn't seem right. I think I hit a button wrong here. 6.67 times 10 to the negative 11 times 10 to the 24th. Oh, it's not squared. Let's see. I got to do my re-enter here. Delete. Let me delete the square. Good. I get negative 6.261.632. And we can argue about significant figures here. Joules. Well, maybe I had to work out the joules. But negative 6.3 times 10 to the 6th. And if you look at your units, this is a Newton meters squared over kilograms squared. This would be kilograms squared. This would be meters. That would cancel off. And so, yes, it comes out to be joules. And I want you to see, number one, it's negative. Number two, it's huge. Is that okay? You comfortable with that? And the truth is, this is the result we're going to have to live with if we are going to use r equals to 0, if we're going to use this from the center. That's just the consequence of it. And I think that's why this particular equation, this one here, out of all the equations I've done so far today, it's this one here that gives students the most struggle. They're all, really, it's negative? Can you have negative potential energy? You can.
You need energy to expand.
Sure. You can. Couldn't we have had it back in chapter 8? I mean, if we had called the ball y equals to 0 up here, what would you say about the ball that is below this point? What kind of energy does it have? Negative, right? So, can we have negative potential energy? Sure, we could have had it back in chapter 8. Now, truth be told, we tried to avoid negative potential energies. We all, oh, let's just take the lowest point there. But there was no reason we couldn't have either all positives or all negatives or a combination thereof of positive and negatives. There's nothing wrong with negative potential energies. What's interesting then is when we use this formula, can this formula ever be positive? It can't, can it? And so I think that's what bothers students when they look at this. And so I like to point it out and keep this in mind, that you see the difference between chapter 8 and chapter 13 is because we put in a different formula, we didn't have to choose where y equals to 0. But here with this formula, we do have to choose where r equals to 0. And when we make that choice, we end up with a formula that always gives us a negative potential energy. So what? You would do the same thing over here. What if you called infinity height y equal to 0? What would that tell you? Then every potential energy would be less than a height of infinity, so every potential energy would be negative. And the lower you are, the more negative it is, and that's essentially what we have here. How high do you have to get, or how far from the Earth do you have to get until your potential energy is 0? Infinite, right? The closer you get to infinity, the closer your energy gets to 0. And so in this picture, this calculator has a negative potential. And as the calculator goes higher, the potential energy is increasing. It's less negative. And it gets higher and higher and higher and higher. And the higher it gets, although it's still negative, it's less negative. And by the time you get infinitely far away, as if you could ever get infinitely far away, but in the limit of getting infinitely far away, how much potential energy do you have? 0. Okay? And so the potential energy is increasing. Don't miss that. It's really not any different. But I think because A, the formula is different, and B, the fact that r equals to 0 has been chosen, and that different formula has a negative in front of it, I think it's the hardest thing of this chapter, is to accept that, hey, that still works. So let's do this example then. As an example here, in a calculation, let's take this calculator. Maybe I'll just erase it over here and say, okay, let's say that somebody throws this calculator with an enormous speed. I mean, let's just say 2,000 kilometers per hour. And so here's this calculator, and somebody goes, I'm going to throw it up 2,000 kilometers a second. Fast speed, right? Now, why did I pick such a fast speed? Yeah, it needs to go out of the atmosphere, right? Because if it was only thrown up at 100 meters a second, it's only going to go up for about 10 seconds. Wouldn't I just use the old stuff we did in chapter 8? All right, so let me change it to you. What I'm going to do is say, okay, so here is this Earth. And here is this calculator sitting on the surface of the Earth. And then it is given an initial speed, 2,000 kilometers per second. So here's the question. How high does it go? How high does this calculator go? How you going to do it? Well, doesn't it sound like a conservation of energy problem? Right? We're given speed, we're asked for height. Sounds like an energy one to me. So let's do that. Let's apply conservation of energy. Let's say that the initial energy is equal to any final energy. And you might even say plus any heat that's created along the way. But just to keep the problem simple, let's say magically there is no heat as it goes through the atmosphere at this enormous speed. Or maybe the reverse. Let's just say this doesn't have an atmosphere. Okay, so it's thrown up. There's no rubbing. There's no friction. And so let's not worry about any heat here. That's not the point of the problem. The point of the problem is get you to use your old stuff together with the new formulas here. Take what we're learning new and say, okay, let me apply this. And again, I'm hoping you're seeing in this lecture, I haven't done anything new other than the universal law of gravity, right? I applied it to some centripetal motion there. I got some period in there. Now I got energy in here. But watch this. Here's what I would do. I would say the initial kinetic energy plus the initial gravitational potential energy would then have to equal to the final kinetic plus the final potential. Does that make sense? And hopefully the only thing you're seeing new here is that we have a different formula. Instead of having an mgy, we have this negative g, m1, m2, and r. But other than that, the technique is exactly the same. Now, like I said earlier, I do have to know a little bit about what's happening to decide if I'm going to use this more general formula or just the mgy. And that depends if it goes out of the atmosphere. And a speed this high does go out of the atmosphere. I wouldn't expect you to know it on the test, that a speed this high goes out of the atmosphere. But if you see anything just kind of suspiciously enormous large, that's the clue. It's like, oh, yeah, obviously. I mean, this is a huge, huge speed. I guess the fallback answer is this would always work. Even if it only went up 1 meter, it would still work. It would be a harder calculation, but it would still work. And so there's no point if it only goes up 1 meter to use the harder calculation. But if you don't recognize it, that's fine. Do this one. But let me put in my numbers here. All right. So I'm going to put in this first one. Here is 1/2. The mass of the calculator as we've been working is 100 grams. And so to get it in kilograms, it's 0.1. The speed here is, and maybe I better watch my units, this is a kilogram, meters per second squared. And so notice I take the 2,000 kilometers per second and I'm going to convert it into meters per second. The potential energy would be this negative 6.67 times 10 to the negative 11. The mass of the Earth, 5.98 times 10 to the 24th. Mass of the calculator, 0.1. Radius, what's my radius here to start? Okay, is it 0? No, so it's back to all this. So this number is going to come out to be exactly the same. So this is the 6.37 million meters equals what? Well, what's my final speed? Zero. Good. Because that's the question here. How high is it going to go? So it's going to go up and up and up and up. And so the conceptual picture is still the same. Is that as it goes up, it is losing kinetic energy and gaining potential energy. At some point, all the kinetic energy is going to be lost, and it's all going to be in my potential energy. And so my unknown is right there. What is my final height? All right, let me put these numbers in, and let me put them in separately so you can kind of see a pattern here. I'll do this one first. This is 1/2 times 0.1 times 2 million squared. This comes out to be 2 times 10 to the 11 joules. Now this number we already did, didn't we? This is, uh-oh. Oh, I said this wrong. I'm sorry. This is way too fast.
Yeah, that's why I thought you did kilometers per hour. And I was like, wait, that's actually too slow. That's really fast.
Yeah, this one's never going to come back. That's not what I meant to do. I want to do that next. My bad. I guess I meant this. I meant 2,000 meters a second. All right, let me make a little modification here. All right, yeah, this one's never going to slow down, which is actually the next question I want to ask here. But let's let this one stop. Okay, so got a little carried away there. All right, so let me change that here. So that should be the 2,000 squared. So we should take off 6 zeros. 11 minus 6, is that a 5? I'll double check here. Yeah, it should be a 5.1 times 2,000 squared. 1, 2, 3, 4, 5. Yeah, so, all right, so this is the amount of kinetic energy it has. How much potential energy does it have? Well, this is the number we already did. Let me not punch it in here again, but this is the negative 6.3 times 10 to the 6th joules. Let me pause right here. Which one's bigger? And I guess I'd say this is more negative than this one. So when you put them together, what's your total energy? It's going to be negative. What does that mean? So your negative energy means there's a solution here. Had this come out to be positive, what are you saying? Yeah, they're saying that even by the time you got a distance of infinity, you still would have to have some energy left as kinetic. And despite me talking all earlier about how this equation can be tough to use because it has negatives in it, now maybe you're seeing a huge advantage. This is really actually a nice equation. What is the difference between a positive and a negative total energy?
One falls back to the Earth.
Yeah, whether it's what we call captured, whether it will ever fall back, whether it will escape or not. And so we begin to see here, and that's why when I got such a big number I was concerned, because I knew this was bigger than this. It would be escaping. It would have more kinetic energy than the potential energy could possibly accumulate even when it got infinitely distance away. And so by the time it gets infinitely distance away, it would still be moving. And so this is going to be nice. Here's what we're really going to be saying. If you want to throw something fast enough that it never comes back, you have to give it a huge amount of energy, right? Its total energy would have to be so big that it would never come back. How big would this number have to be? 0. Now, I admit, doesn't that sound funny? The total energy would have to be so big it would never come back. Its total energy would have to be 0. You see, this number being negative and being very negative is very useful now at this point. What it says is something to escape, something to never come back means it's got to have positive energy. Anything less than positive means it is going to eventually get to a speed of 0, but not be infinite away, and then it's eventually going to get pulled back. And so that's how we're going to talk about whether something escapes or not. Now, this one does not escape, so that's why I wanted the lower number here. In the next calculation, we'll do a higher number here. But what this is saying, if I put these together here, I get a negative I guess that 2 would fit right here. And so it would be a 6.1 times 10 to the 6th joules. Right? That's what that's saying. And so that's the total. And again, is the total positive or negative? Well, the total is negative. Simply put, we've got a lot of negative potential energy. And the only way we're going to escape is if we have more kinetic energy than we have potential energy. The total's got to come out to be greater than 0. And it doesn't. And so this object is not going to escape. It's going to go up to some maximum position. And that's what I'm trying to solve here. So what is that maximum height here? All right, so as I work it out, you'll see I got a negative here and a negative there. Good, those will go away here. Let me take this first number, which is the negative 6.1 times 10 to the 6th. Let me bring these guys over so I can divide it by 6.67 times 10 to the negative 11. I can also divide it by 5.98 times 10 to the 24. I can also divide it by 0.1 and I get some number. Take the reciprocal of that. And if I've done all my math correctly here, I get 6, 5, 3, 8, 7, 8, 6 meters. Or maybe just watching my significant figures, let me call it 6.54 million meters. And so that's what it's saying. But of course, this is measured from the center of the Earth. So if the question is how high does it go, what do I need to do finally? Yeah, and so back to this picture, which I guess I've erased, but maybe I'll use this one. This might be its height, and this would be the radius of the Earth, or its initial height in this case. So h would be my final height minus my initial height. So in this case, 6.54 minus 6.37 million meters is my calculation. So the millions go away. I guess I need to borrow from the 4, so that's a 7, that's a 1 million meters, so 170,000 meters roughly, and probably should have been more clear with my significant figures there, but this is going to go pretty high. High enough to justify that potential energy. How high is 100? Yeah, that's high enough. We better, you know, we still getting over 10,000, 12,000, 30,000. Well, I don't know. The atmosphere might go. If we call it 100 miles. Yeah. Yeah, it's still we better use it. All right, anyway, so it did go high enough. So I wanted to make sure I gave it enough speed that it would be justifying using that equation. But even if I didn't, it still works out there. But you see how you kind of set it up here. Now, why don't we go back and try another problem? This problem, why don't we do the number that I made the mistake on? Why don't we try that number? We could ask ourselves, what would happen in a problem where we gave this calculator the 2,000 kilometers? I mean, that's a huge speed, right? What would happen there? Well, I guess we would start off with this equation where we would have the 0.1 and now we have that 2 million. And that might be even too big for you to kind of see here what's going on. Didn't we get like 2 times 10 to the 11th, if I remember right? It should be 3 more zeros squared, so 6 more zeros. So that's how much kinetic energy we have. The potential energy would still be that 6.3 million joules. Oh, well, that's so small that that's not even going to matter. Bummer. All right, either way, that's just a terrible number. I should have never come up with that number. All right. So why don't we do about, I think around 14,000 meters per second might be a good number.
You would have to use relativity. That's 2,000 kilometers per second.
Oh, 2 million? No, we're not at relativistic speeds yet. Because usually we go relativistic at 10% the speed of light. So anything with 10 to the 7th in it. So we're only 10 to the 6th. So anyways, let's try a much lower number here. And so let's see what this energy gives me. So let's say we throw it up, certainly at a much greater speed than the 2,000 meters per second. But 14,000 meters is not such an overwhelming number, and you can see it. Not to say that we'll actually do it, you know, but this would be the speed just to see some of the numbers. So 1/2 times 1/10 times 14, 1, 2, 3 squared comes out to be 9, 8, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 1, 2, 3, 1, 2, 3 joules. So this is 9.8 million joules. So when you take a 9.8 and you subtract a 6.3, the total then is 3.5 million joules of energy. But I want to pause right there. Positive number or negative number? It is positive. What does that tell you? Yeah, it's telling you that this thing's never going to get to the point where it will stop. There is no place where you could put in an R value and have a 0 speed. Because this always gives us negatives, and this always gives us positive. And again, now maybe you see the opposite of this equation. This equation is very useful because negative numbers and positive numbers play a significant role, and they help my understanding of them. So I'll say it again, as funny as it sounds. If you want something to go so fast that it never comes back, you got to give it a lot of energy. Its total energy would have to be 0. Okay? And so 0 is a lot of energy because we're starting with such a large negative amount. Okay? So obviously the 14,000 is more than enough that it would never come back. The 2,000, it would come back. And so this begs the question, what is just enough to escape? How much do you have to have? But we'll finish this calculation before we do that. Let's come over to here. Because I would say then that if I really wanted to know what would happen in the long term, this is what I would put on the other side of the equation. On the other side of the equation, I would say, since this number comes out to be positive, it is never going to come to a stop. And what's going to happen then is it's going to keep going until it is infinitely far away, which, you know, depends on what you mean by infinitely far away. Obviously, you never get there. But at some point, you would say, you're so many millions and millions and millions of miles out there that this is essentially 0. How fast is it going? And so now we can set this equal to 1/2 times 1 times the final speed squared. And here's what you're really saying. You're saying that this calculator would get so far away that it's essentially out of the sphere of influence of this planet. And it's not slowing down from that planet anymore. Now, there could be other planets that are speeding it up or slowing it down. But if that was all there was in this universe, then this thing would just keep going that way with that particular speed. Which is what? And so if I take 3.5 times 10 to the 6th million, I multiply it by 2, I divide it by 0.1, I take the square root of all of that, and I get about 8,000. And so my final speed here is about 8,300, well, I'll just round it to 8,400 meters per second. So that's what it slowed down to. And so as it was moving away, it got slower and slower and slower and slower. Which I can't help mention this. You may or may not know, because in terms of science, it's relatively new discovery. I mean, if you think about all this, this is what scientists thought for years and years and years about our galaxy, right? There's this big bang, and one galaxy goes this way, and another galaxy goes that way. So here's the question. As they move apart, will they come back together? I mean, what is their speed? I mean, if their speed is slow enough like this one, what's eventually going to happen? Well, eventually they'll come to a stop, and then they'll come back together. And so the Big Bang will become the Big Crunch. Or perhaps maybe it's different. Perhaps it's this scenario. Perhaps it's this one where we start off with this Big Bang and they're going so fast that even though they're slowing down, they don't slow down enough, and so they keep going forever and ever and get further apart, and we call this then the Big Freeze. So the Big Bang becomes the Big Freeze. So there was a question for years and years. Does the Big Bang become the Big Crunch, or does the Big Bang become the Big Freeze? So question is, well, let's measure these speeds, right? If we could accurately measure these speeds, we would be able to answer that question. And so starting in the mid-90s and the late 90s, the first experiments came in the late 90s. You know what they found? Was it this or was it this?
Neither.
It was neither. They found that they weren't slowing down at all, but they were getting faster. And I can imagine when, you know, that first data came in, they looked at it like, your partner made a mistake. This is just not right. There's something your partner did wrong here. Try it again. So they did, and they made it again and again. But finally, by about the year 2000 and 2002 and 2003, you know, those in the know were convinced, hey, it's expanding out. Why? Well, don't know the answer to that one. That's the next step. But at least it's not this scenario. And so we have a very different view of our expanding universe because of that. So this is not either one of these options. Well, like I said, let's do a third calculation. And the third calculation is really the one I wanted to focus on. What would be this magical speed? If you were on the surface of the Earth, how fast would you throw this calculator so that it never comes back? What would be the minimum speed? I mean, this is obviously more than you need, right? This is still moving. And so what are you saying? You're saying, well, if I have a 1/2 mv squared for my initial energy, and I add it to the fact that I'm sitting on the Earth at some initial height, which is, again, the radius of the Earth, then this number right here, I'll put in my mass, I'll just leave it as a symbol for a second, but this then would be what we will call its escape speed, ES. What is enough speed do you have to get it? And like I said, looking at our numbers, it's very clear that it's got to be more than 2,000, but it's got to be less than 14,000. All right, so what is it? And so here's the radius. What does this side of the equation? This is really the key. If all of this was beginning to make sense, what do I put on this side of the equation? 0. Because what are you really saying? You're saying, number one, it has to go all the way out to infinity. How much potential energy does it have? 0. And it just barely gets there. So what speed does it have? 0, right? So it has 0 kinetic, 0 potential. Total is 0. That's what you're really saying. You're saying, how much energy total do you have to have? How much speed do you have to have so that the total energy comes out to be this enormously large number called 0, right? And it makes the math really nice. And so, like I said, I like to start this with showing the students that, hey, you might be a little bothersome by this new formula. And there's some negative things about it at first sight. But now you see some real advantages of this, and this is a good key issue. It's just set equal to 0. And there's nothing better than solving the equation with 0. The homogeneous equations are much better to solve here. In fact, if we go through this, we'll see that the mass of the calculator cancels off. So in other words, whatever speed I need for my calculator is also what I need for my rocket, which is also what I need for my roommate, you know, never come back. So it's the same speed, okay? If I go through the math then and figure out the escape speed, I get this 2 I get a capital G, I get the mass of the planet divided by the radius of the planet, and then the square root. Okay? And so that's what I would need for that planet. Now, I say that planet, but this lecture I've been doing Earth. So let's do Earth here. Let's put in the numbers here for Earth. What would escape from Earth? And so 2 times 6.67 times 10 to the negative 11. Fix that there. Okay, then times the mass of the Earth. 5.98 times 10 to the 24th. Divided by the radius where we start, which in this case is on the surface, so radius of the Earth. So 6.37 times 10 to the 6th. Take these square roots, and I get a little over 11,000. And so 11,200 meters per second. And so that's what we like to say the escape speed is. If so something is going that fast, it's not going to come back. That's Earth. Could we do it for another planet? Yeah. So even though I've done it for Earth, I bet you could also do it for Mars. Is always a fun one. What's the escape speed of Mars? Or the Moon? The Moon's a fun one too, because the NASA and the early scientists were very concerned about this. I mean, you come down, it's such a low escape speed that if you come down too hard and bounce, you can actually be above the escape speed. So you bounce off and bye-bye, you never come back. You know, and then, they were wondering, what if, the astronauts jumped? I mean, could there be some kind of, it turns out jumping, there's no way they're going to jump and leave it. Some of the scientists, or the astronauts when they were on the moon, they were trying to do it with golf balls. So they'd put a golf ball and I don't think they ever got it enough. I think it eventually landed back down, but it's a small speed. I like to do Mars for a different reason. So let's put it, yeah, I don't even think it made a whole orbit. That'd be interesting, but still, but if we put in our number here for Mars, like I said, Mars is kind of a fun one for another reason I'll mention here. But 2 times 6.67 times 10 to the negative 11 times the mass of the planet. So let me look up Mars here. And so Mars is 6.42 times 10 to the 23rd. It has a radius of, so divided by 3.37 times 10 to the 6. Take the square root of all of that. And it's still a pretty good sized number. But as you might guess, much smaller than the Earth. Now, why do I bring that one up? Well, turns out that when things, particularly Mars, which has no atmosphere, and the asteroids come in, these pieces on the explosion when they hit are going pretty fast. Now, most of them, when they bounce off, especially onto Earth, are much lower than this. Because first of all, it got slowed down as it burns through the atmosphere. Then it's got to get slowed down as it goes back out to the atmosphere. And this is a big speed. But what about Mars? Mars, that's not an unreasonable number for an asteroid to come in. So when an asteroid comes in and hits the surface, things can come ripping off of there, 6,000 meters a second. Not uncommon. So what would happen to those objects? Right, they would fly back out into space, maybe get pulled inward from the sun. So what's the next planet they're going to hit? The Earth. And so it's not uncommon for us to find asteroids that were what? Pieces of Mars. And so NASA, some questions still in their mind, but they very much believe that they have found many asteroids coming from Mars. The makeup, the structure, it all makes sense. It all adds up. Now, sometimes it can get difficult to find these because, if a rock falls to the ground, and it was 1 million years ago, how do you know that rock came from Mars? So where do they find these? They're looking for them right now. Yeah, this is a really good time to look for them. because it's the summer in Antarctica. So you got 9,000 feet of ice. You find a rock on top of that, where did it come from? Space. Right? And so this dark rock on the white ice is easy. So they'll be flying, they'll be scouring, they'll be looking for these little chunks of rocks. And then they get them. And they're all because of this escape speed. And so then they can analyze it. And so maybe you've seen their pictures where they think they might have found some kind of fossilized ancient life, very debatable. So who knows? Because they're very different. But the point is, how do they even know they got a rock from Mars? We didn't go to Mars and come back. I mean, we put some rovers on there, but they didn't come back. They just go down there and dig and do their experiments and send the data back. But we don't have any rocks. We've only been returning rocks from the moon. That's it. And so this is a good, bit of astrophysics or astrobiology, if you will, which is a very interesting title. Astrobiologist, and so, but there is.
Then wouldn't it just be like stuck out in the middle of nowhere because it would lose all its velocity, but not have any influence to be pulled back?
Right. So then it would kind of get pulled in towards the sun, and then the orbit of the Earth would come along and pull it in. And then you would see it as a shooting star. And so that's what all of our shooting stars are. Not necessarily from Mars. Most of them aren't from Mars. Most of them are pieces of rock, usually from the asteroid belts. You got a bunch of asteroids out there and they bump into each other and the rocks go in different directions. Or old pieces of comets that, in fact, isn't that what there's a great one coming up. I forget the exact date, but it's an old comet, is right here in this path, and it went through and the heat from the sun kind of disintegrated. So there's all these rock pieces, and so every December, early December, we go right through that debris. Yeah.
Okay, huge one almost hit the Earth or came really close.
Oh, that was last week. Yeah, there was a big, the size of an aircraft carrier.
They said like it came between the moon and...
Oh yeah, there's the moon, the Earth. It was, now I forget where it was, but it was
small between those.
So, but the size of an aircraft carrier hitting our ocean would probably wipe out 1 billion people. We got 6 billion, 7 billion I think it counted, right? So, what's another billion people? But, so they did calculate this really carefully and try to figure out where it came from. Now, let's change this a little bit. I've been dealing with this one, and obviously I have spent the most of the time in these 2 hours talking about this equation, because again, I think that is the hardest one to do. But let me change it to this. Let's not talk about just shooting something straight up and seeing if it comes back or doesn't come back, or what is the minimum speed needed to come back up here. Let's put something maybe a little bit more practical in here. What if we're going to build a rocket and we want to put, say, a weather satellite up, or a spy satellite, or a GPS satellite? How much energy do we have to give it?
Just enough. That's how far we want to go.
Okay, it would depend how far, but let me ask you this. Would it ever be more than 0? No, right? So we don't want it to completely escape. We want it to go up, we want to give it enough energy, but not quite 0. So, how much? Well, as you said, it depends on how high we want to go with it. In fact, we already did this calculation. Let's write it out again. Could you tell me what speed the satellite would have to be going? Well, here's my G, my M1, my M2. Here's my M2, here's my V squared over R. So about an hour ago, we did this one, right? We said, look, let's take the Earth. Here's the Earth. Here's the object that's going to go around. Again, either a natural or an artificial satellite here. But if it's going to go around in a circle, I will take my centripetal forces from Chapter 6 together with my new universal law of gravitation. I will cancel out the R's. I will cancel out the M's. And I will get a speed of the square root of G M1 over R. And so that was a formula that we had quite a while ago here. As we said, this would have to be its speed. And we got in that little discussion, which would be going faster, the International Space Station or the moon. And you can see because of the R, clearly the International Space Station has to go faster. But does that mean it needs more energy? Which would need more energy? The moon. Why? Okay, fair enough. It has more mass. Let me rephrase that. For the same mass, would further away need more energy or would closer in? Now remember, closer in is going faster. But further out would be what? More potential energy. Does that make sense? So I want to make sure this is clear, because you can miss this very well. What I'm saying here is the one that is close in is going to go fast compared to the one out here. It's going to go slow. So the one that's going to go fast, you're going to say, hey, that needs more kinetic energy. But the one that's further out and further up, it needs what? More potential energy. So what does the two come out to be? And it turns out that the further you go, the more energy you need. So it does take a lot more energy to go further out. Not that you have to go as fast, but because you have to go so far, your height is so great that it takes more energy. So let's go through this equation. How much energy would it take when I am way, way out there? And it turns out to be quite a bit of energy, which answers maybe another question for you. How come we launch, not all, but many of our satellites in the southern part of the United States, either out here in Vandenberg or particularly Cape Canaveral?
Well, I thought it was next to the equator because then it has the most speed without.
So why do we go as far south as we do? You got the idea. Closer to the equator. Why does that matter? Okay, I'll agree that there's a little oblong shape to it. That's not the main reason, though.
The object's already going up faster.
Don't forget, the Earth is spinning. It's spinning to the east, right? It's easy to forget right now, but as we sit here in this room, you and I are moving to the east, 800 miles an hour. Now, we're all going together, so it's kind of like we're riding in a car together, and, you know, we don't think about that high rate of speed. That wall is moving at me at 800 miles an hour. Now, it's a good thing I'm going that way at 800 miles an hour, and the same thing with that wall. And so we're all going really, really fast to the east. So, since the difficulty of getting something in space is either giving it, you know, enough energy, that is enough speed, why don't we take advantage of the fact we're already moving that direction? So if you look at a globe that is spinning to the east, which would be the easiest orbit to set up? One that goes to the east. You're already moving to the east. So if you look at a globe, and as you go further south, at least in the northern hemisphere, closer to the equator, I guess it would be further north in the southern hemisphere, but as you get closer to the equator, aren't the parts on the equator going a further distance and therefore a faster speed? So down here on the equator, it's over 1,000 miles an hour. By the time you get up here at 34 latitude, we're down to about 800. And of course, if you got all the way up here to Alaska, it'd be much slower. If you got at the North Pole, you would be going a speed of 0, right? And so the surface is traveling at different speeds. So the idea here, and the whole idea of why the United States decided to put its Gemini and its Mercury and then the Apollo missions and launch them from Florida, is you are getting further and further in the south. It also helps with a number of other things. It's to the east and you got water over it. You got the Azores for an emergency landing spot. You know, there's a lot of other neat little things here. But the idea of going to the east is what makes it very plausible. So the first and easiest launches are to the east. Vandenberg shot one off not too long ago. It was right at twilight, so I was able to see the jet. But it wasn't. It was a polar orbit. You could actually see it come up, and the idea was to go over the North Pole. In fact, that's what the purpose of the satellite was. It was to study environmental effects at the North Pole. So they wanted this polar orbit. So the idea of having a speed to the east wasn't that significant. So they didn't launch here. They launched at Vandenberg, which a lot of ours is in Vandenberg. There's a company, a private company now, as the world is changing, and it's less being launched by governments and more being launched by private enterprise. In fact, you probably know we don't even have a space shuttle program anymore. You know, I mean, who's going to be firing these rockets in the future? And it's really private companies, right? And these private companies are coming out. Who's that guy who flew the X plane and got the X Prize? Is it Rotan?
It's like that.
Yeah, I'm pretty sure it's anyways, he got the $10 million for being the first commercial one to go up in space in so many days, and they're making that. Anyways, they're making the first spaceport there. I think it's New Mexico. Anybody know? You can ride into space for $100,000 in a few years or something here. And so if you got an extra $100,000 lying around there, you can buy a ticket. So that's their goal there, and I believe it's out of New Mexico. I should look at it. But there's another company that you may not be aware of. Unfortunately, they kind of went bankrupt these last few years, so maybe it wasn't very successful. But they call it Sea Launch. It's in Long Beach here, California. What do they do with it? What's their strategy? Well, they have a big barge. It's actually an old oil rig out here. And they float it or drag it with tugboats down to the equator. Why?
You save money.
Yeah, it's actually going to save money. I know it's a lot of work to put it on a tugboat or put it on a platform, tug it all the way down to the equator. But the amount of payload you can get makes a huge difference. So I'll be interested to see if anything like that comes back. I think Brazil's got the best idea. They're building like crazy. Guess where they're building?
Right there.
The mouth of the Amazon. Right there. They're building a whole launch platform, high tech, because they're looking at the future of the market. They've got a huge challenge though too, because their industrial might is down here. How do you get it from there to there? Well, they tried to build a rail system, but the soft ground of the Amazon, so they're having to do it all by ship. So they got their challenges. The French, where do the French launch? French Guiana, right, down here. Right, too far north to be real successful. Or my favorite's the Russian. What do the Russians do? Well, they do get into the lower part of their country, but then they just make big rockets. I mean, that's why they've got the biggest rockets in the world. It's like, we just can't go that far south, so we're just going to have to build a bigger rocket. So maybe I'll stop there for time, but when we come back on Monday, we can answer that question. What is the energy needed here for this launch?